Hi, everyone. I thought I would record a video of me solving two problems that I did not have time to solve in the problem solving session today. So let me share my screen, and I don't think it'll take too long. Here's one of them. This is a simpler version of something the professor proved in lecture, but sometimes the lectures can be so heavily formal, it's kind of hard to see the forest for the trees. So I thought I'd bump down to just 2 dimensions. And what we're claiming is that if we have the projection map that takes me from some product space, so I sketched some product space here, to one of the component spaces, here, the space X, then apparently it's continuous. So just to get an idea, I'm basically saying like, okay, this squiggly line is the space X, the straight line is the space Y. So the Cartesian product is sort of just extruding that squiggly line up. And so I'm projecting all of that basically just onto the X component. So I've written out one of our definitions here, and we have a bunch of equivalent definitions for continuity, which is why things can sometimes get confusing. But the one I'm going to use is one of the nicer ones. It doesn't involve any epsilons or deltas. It just involves neighborhoods and pre-images. So it's a new definition. You guys probably haven't seen this before lecture. But it's handy, and it's going to extend into topological spaces really well. And proofs of continuity in topological spaces are generally super clean, at least compared to the epsilon delta proofs we're used to from analysis. Okay, so we have this map, this projection map. And I say over here, recall that a function's continuous, so in this case, P is continuous, at a point if no matter what neighborhood you take in your codomain, it pulls back to a corresponding neighborhood in the pre-image. So that's our definition. Let's work with it. I want to say I'm continuous at this point, so let's just establish that that's a point in the product space. So AB is in X cross Y. Maybe I'll put it right here. And let's also say we have some neighborhood M be in the system of neighborhoods at the projection point PAB. Right, so P is actually going to take this point X comma Y, and it's going to just map it straight down to that point. So I'll put that here. That's actually X, right? The projection map just takes the X coordinate, but I'll write it both ways just to keep in mind what's happening. Okay, so I mean, the first weird thing is this notation. Professor likes using that because it helps with formal logic proofs. Usually we'll just say M is a neighborhood, and we'll write it in English, a neighborhood around the point P of AB. And maybe I'll just say by the definition of P. Let's actually write it out in English. By the definition of P, M is a neighborhood. A lot of times mathematicians get lazy and just write NBHD for neighborhood. Say a neighborhood of the point PAB, which is just A. Yeah, so my bad, I was using XY over here. I don't know why, but it should have been A's and B's. No big deal, hopefully. Hopefully you caught that and corrected it before I did. Okay, so we have that, right? We've established, okay, we have some point, we have some neighborhood of that point. My goal then is to show this. Right, I want to prove an existence statement. I want to find a corresponding neighborhood. Maybe I can just go ahead and draw the neighborhood we found on here. Maybe this is M. So that's M in yellow, maybe. And apparently I need to mess with the pre-image of M and show that what I get contains a neighborhood of the point AB. So the pre-image of M is going to be pretty nice. I mean, that's just, it's a projection map, right? So you can just look, I guess I don't need all those dots. The pre-image will just be all points that map onto that little squiggly open interval, right? Maybe I'll shade this in. So that's the pre-image of the neighborhood M. Cool. So let's actually write that down. So the pre-image of M, let's actually just say what it is. By definition, that's the set of all points. And I guess now I'll use XY because I haven't yet. Set of all XY in the product space such that projection lands in M. But of course, we know what the projection is. P of XY is just X. And with a little bit of work, maybe it's good practice to verify this, but hopefully you'll believe me, at least based on the picture. This is actually just M cross Y. All we did was take that little sliver M and extrude it along the Y axis, basically, along the space Y. Okay. And so that's our pre-image. And we're actually kind of done here. There are probably a couple theorems we could cite or something, but I'll just say, note that M cross Y is actually a neighborhood of AB already. So it's a neighborhood of AB. And I suppose you could prove that, you could, find some delta so that you can fit some open ball around this point, right? And I guess the open ball would be more like a product. It's more like a square because we're in the product space. Depends what your metric is, but it's usually what we do for simplicity. So what was I saying? Find delta greater than 0 such that, this ball around the point AB of radius delta is contained in the pre-image. So contained in M cross Y. But that's not too hard to do, right? We already know that M itself was a neighborhood, so you had some other delta or some other epsilon, whatever you want to call it. And that pretty much handles it. So that's all you need. And this is going to generalize when we reach topological spaces. And it's going to be pretty nice. We won't even need to talk about like this part of it. All you'll have to do is look at a pre-image and say, okay, it pulls back to a nice set in the domain. Okay, so next one is something involving the diagonal map. This is a fairly common proof that you see in like intro topology, but we've established some other theorems that can help us prove this in a pretty quick way, actually. But mostly I want to show this because we haven't seen the diagonal map yet, and it's relatively important. Basically what it says is, okay, if you have some space X, the diagonal map is, well, it's called the diagonal map for a reason. Uses delta, Greek D. And it maps it to the product space of X with itself. So there's X cross X, right? And what happens is any point X, let's say this is little x, will get sent to, okay, here's X on each of those. And it gets sent to X comma X. Now, if you do that for all points, the image of the entire domain, the range, ends up being a diagonal. All right, so you get something nice like that. I've included a weirder picture up top. So let me erase this and show you a weirder picture. Again, because if you're watching this, maybe you just want to see cool things in topology. Maybe one thing you haven't seen, or maybe you have, is how to represent a torus. And you can actually represent it as a product space. So if you start with, this is, we'll say the unit circle, and you can say it's an R2 or in the complex numbers or whatever you want to call it. Imagine there's some axes, right? So we label that S1. It's a sphere in one, it's a one-dimensional sphere because it's a curved line. And apparently S1 cross S1 is the torus. Okay, it's a little weird to prove, but maybe you can believe it. Usually when you say circle across a circle, people think of a sphere. I don't know why that's the natural thing to jump to. It's the natural thing my mind jumped to when I first heard it back in like undergrad, but it's actually a torus in the sense that, okay, you have S1 as one of your dimensions. So that's say like this little circle right here. And you're taking the Cartesian product with another circle. And so basically what's happening is that every point of this bigger circle, you're attaching a smaller circle. Right? So you go all the way around and eventually come back. And you're just attaching a bunch of circles around a ring. And that gives you a torus. Right? So anyway, that's a product space. So you might think, what does the diagonal map look like? Right? So I start with a circle. I apply the diagonal map. What happens to that circle? Right? We just saw that if I'm doing this, going from a line to a square, then the diagonal map is a diagonal line. What about here? Well, it's sort of like, let's say this is the origin. Why not set it anywhere you want, really? And then let's think, okay, as I, let's say this is like my starting point on the circle. If I go like a quarter turn, maybe call that X. So I go like pi over 2 radians around the circle. Well, I'd have to go to pi over 2 comma pi over 2 on the torus, okay, which is weird to think about, but that means go halfway around the circle and also halfway around or, pi over 2, so a quarter way around the other circle. So you go pi over 2 units around each circle, and it kind of traces out this kind of looking thing. Okay, so let's draw that without the other 2 lines. So I'm, going a little bit in each dimension. So I land on top of the donut. And then, okay, I come over here. Okay, so that's like X comma X on my diagonal map. Let's say I get to point Y. Okay, that's pi radians. So I have to go, another half turn. So I come all the way around here. And let's draw this better. Yeah, no, that was fine actually. So, and now I'm like on the inside. That looks good. So I'm on the inner wall of this donut. I'm made like half a revolution. And then I keep going right over here. I guess I end up on the interior wall. But I should be lower, shouldn't I? Yeah. Right, because by this point, the third point will be on the bottom and this far around. So if you imagine, okay, here's a little ring. I want to land like here. So let's keep that point there. So I come and then just kind of behind. And then I come out and connect back up. Right, so I make this like revolution. It's actually a perfect circle in its own right. But that's what the diagonal map looks like on the torus. There's a fancy name for this particular slice of a torus. I forget what it is. It starts with a V. Anyway, not important, just showing you can do weird things, and tori are fun. So there you go. How would we show this map as continuous, though? Well, hopefully with these couple examples I've shown, at least these like geometric examples, they're building your intuition and saying, some of this. That yeah, if you start with 2 points that are close together on the circle, or on whatever space you're working in, they'll, land close together in the product space. And that's what continuity is, right? It says if you take 2 points close together, they stay close together. They don't split apart. So let's actually sit down and prove this. And what I've written up here is we actually have an established theorem we can use. I know that if I have any function, here I'm just calling it f as a placeholder, from some space to some product space, and looky here, the diagonal map goes from some space to a product space. And I know that map is continuous if when you compose it on the left with any projection map, if that is always continuous for all possible projection maps, then you're good, right? So all I have to say then is consider the projection maps. So this ends up being true. Consider the projection map. Let's call it P1. That goes from, right, you have to start in your product space, and we're mapping to the first component. The first component is just X. And so that takes, I guess I should say X comma Y, thinking of diagonals, takes any point in the product and maps it to the X component. And I mean, might as well always also look at P2, right? So X comma X down to X, mapping X comma Y. This time it projects onto the Y component. And you might think of what these projection maps look like on a torus. Kind of unfolds it in a weird way. But anyway. So we're considering those projection maps, and I want to show that P1 of F is continuous and P2 of F is continuous. Let's do that. So P1 composed with F. Well, we're really thinking about the diagonal map, so P1 composed with delta, and we'll say of X, right? That's the same as P1 of delta of X. But delta of X is just X comma X, right? The diagonal map just maps to the pair. And we know projecting, I forgot my P1 here, projecting that gives me an X. So it certainly looks like this is the identity map, right? It takes X to X. It's true for all X in X. And if I did it with P2, you should not be surprised to see the same thing happen. P2 of delta of X is P2 of X comma X. And it doesn't matter which component I'm projecting on, they're both X, right? So I get X. I'll just say that is both P1 composed delta and P2 composed delta are identity maps. And the professor also proved identity maps are always continuous. So which are continuous. Therefore, delta is continuous. And okay, you don't have to prove it this way. There are numerous other ways you can prove that the diagonal map is continuous. But this goes to show you that not everything we're proving in lecture is frivolous and useless. I think there is actually a way to apply these things. And I don't know, I don't think this is particularly difficult, right? You only had to worry about two maps. They both end up being the identity. It lets you handle, a type of function you've maybe never seen before that can have weird geometric interpretations behind it. So cool, that's all I wanted to do. I'll upload the rest. If you weren't in office hours tonight, then feel free to read through them on your own time. There's quite some good stuff here relevant to the homework. So yeah, hope this is helpful. Thanks for watching.